Hi. Thanks for sticking with me. I really needed that vacation. Needed to clear my head a little bit. I certainly got an opportunity to do that. So, after reeling a little bit from that EEPROM replacement issue, I want to get into some power issues. I don't believe that this is going to be any simpler to solve, but I definitely want to try to quantify this and potentially take a stab at trying to solve it. I want to be able to figure out the right way to measure the problem. And I believe I've even got a permanent solution in my mind on how to solve this problem. We'll get into that a little bit. I do still have some control logic timing problems and instruction timing problems that I do need to get to, and those need to be solved before I can move forward. So maybe this will be a quick video, maybe this will be a long drawn out video. I'm not exactly sure where it's going to go yet, but let's get right into it.
Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey.
Okay, in previous videos, I had problems with the system going into reset, and I glossed over it very quickly and switched back to a different power supply. Ultimately, my goal is to power the entire build off of this USB connection. Now, USB is going to deliver exactly 5.0 volts. Right now, I've got it powered by this wall wart, and the wall wart itself is putting 5.2 volts. I'm still getting 5.2 volts. Now, that's without any kind of resistance load or load resistance. So when I plug in here, I'm getting almost 5.1 volt. By the time that gets down here to the power supervisor, I'm right at about 5 volts. Now, if I switch my power from the wall wart to USB, you can see it never comes out of reset. Well, why doesn't it ever come out of reset? So if I measure voltage very carefully here, 4.81 volts. If I measure here, 4.78 volts. If I measure down here, 4.72. And again, if I measure across this power supervisor, I'm at 4.67 volts. Well, that's right about at the threshold. Let me pull up the data sheet and I'll show you. Okay, so here's the data sheet for the LP3470, and there are several flavors of this that are available. So in the detailed description, the reset threshold options are these, and I picked up the 4.63 volt option for the threshold. So what does that mean? Well, if I look at this reset timing diagram, there is a threshold voltage that comes across the top up here, and then there's a hysteresis or hysteresis voltage difference allowance. And if you look at the first one, it comes out of reset some time after the voltage climb passes the threshold voltage. So that's the threshold voltage at which that timer actually starts, and that's controlled by the capacitor that's associated with it. When it drops below the threshold voltage, less this hysteresis voltage, you'll see that the reset is pulled low, and therefore the circuit is in reset, and once it comes back up above the threshold voltage again, it starts that timer, after which reset comes back high again, pulled high by the pull-up resistor. But if the voltage drops but doesn't go below threshold, then it does, or threshold minus this hysteresis voltage, reset will go down a little bit, but it won't actually go into reset. The reset voltage will go down a little bit, but it doesn't actually go into reset. What that's telling me is that at 4.63 volts, I am below that threshold. And looking at the data sheet here, my threshold is 4.63 volts. The hysteresis voltage is 35 millivolts. What does all this mean? Well, what it means is I'm actually losing voltage between where my power input is and where I'm measuring my voltage. If I was measuring my voltage right up where the power input was immediately, I don't believe that I'd have a problem, but the circuit itself might not work well either. Since I'm measuring the voltage with the power supervisor quite a ways away, there's some voltage drop that's taking place there. It's putting me below the threshold. And I think that's probably a reasonably good thing for me to be measuring, not right at power input, but somewhere a little bit distant away from that so that I can keep track of it if I'm going to run into a problem. But the question then becomes, why am I losing voltage across my build? And that is really the topic I want to tackle today. Let me bring up the PCB design for the register backplane. All right, here's my register backplane PCB. And one of the things I think I've got a challenge with here is if I zoom in here, my VCC traces here are 0.3 millimeters in width. If I use the reverse accent key or the grave key or whatever you want to call that, what I've done now is I've highlighted everything that is related to power on this PCB, and hopefully you can see it all. But not only do I have relatively thin traces, but I don't have it actually connected in a loop all the way around. So I get down to this point here for register C, and it doesn't connect off to register D unless I have a board here in position D or position E or position F. Power actually has to come from this point up here at the top, all the way around down the left side of the board, all the way across the bottom, and then back up the right side of the board in order to deliver power to these outside connectors, which I'm using to power the rest of the build. So that actually is detrimental. The entire length of that trace is rather long. But if I take any one of these traces and look at them, they're all 0.3 millimeters. And I'm going to say this board is about, I'm not sure, about 20 inches long. Let's see here. Switch to inches. Height 19.1. So all in, we're looking at 24 to 25 inches of tracing. Power input point all the way down here to the bottom and deliver power to each of the locations. The challenge is I did not make this a 4-layer board, and I believe I probably should have. I probably have the ground plane handled better. So I do have a ground plane fill, and I've got it stitched together pretty good between the front and the back copper. So I don't believe that's going to be a problem, but I do believe that power definitely is a problem. Let me show you what I'm thinking about here. Opening a calculator tool, if I assume that I've got 1 amp of current and I want to tolerate a 10-degree temperature rise at 20 inches in length, it says my trace width for external traces should be 0.3 millimeters, which I've got. But look at my voltage drop that I can expect. I believe that is my problem. I believe that the trace width was adequate for the temperature rise that I wanted to be able to tolerate, but the voltage drop is not what I wanted to be able to tolerate. Okay, so what's the solution? The solution is to make this a 4-layer PCB and reorder it, which I need to do, and I'm going to do. And there's a few other things I want to make changes to. So let me start by converting this to a 4-layer PCB and get that dressed up. And once that's done, I'll talk through some of the other changes I need to make. The first order of business here is to convert this to a 4-layer board and then set the 2 internal layers to be VCC and ground and fill those with copper. Next is to separate the chassis ground from the electrical ground and separate those with a reasonably high value resistor. Finally, it becomes a matter of going through and methodically cleaning up the printed circuit board. There are a few things that I wanted to make sure that I took care of. The first of which, I didn't want to keep the VCC and ground traces on the outer layers now that I have entire layers internally dedicated to both VCC and ground. So I went and removed them from the outer layers. The next thing I wanted to accomplish was I wanted to move the connectors on the outside of the board out 1/10 of an inch away from the center of the board. The connectors that I have are just a hair too tight to fit in there. I was going to have to shave or sand them down a little bit in order to get them to fit properly. This just solves that problem without any extra work. And then it's just a matter of going through all the design rules checks and making sure that I didn't actually create any new problems. All right, finally, is this going to be version 1.1 or 2.0? I haven't fundamentally changed the interface to the rest of the build, so I'm going to call it 1.1. The last thing I wanted to do to the backplane is to create some holes for some standoffs. Now I've put drill holes in for a number 4 threaded screw. But the challenge I have is the head of that screw may or may not encroach into other areas, and I'm not sure that I've got that in the best position. So this is more or less an experiment for me, just to see if what a standoff screw hole would look like and how I could go about getting that attached. The plan is to use likely nylon screws on top so that I might be able to have the opportunity to whittle that down a little bit or reduce the size of the head of that screw. I may or may not use those, but I wanted to call it out so that there wasn't any surprises when the new Register Backplane shows up with holes in it. Here we have an unusual view of my workspace, and I've got well, I'd like to call it a laboratory power supply, but in reality it's just this cheap Chinese POS that has the ability to current limit and voltage limit, and that's about the extent of its abilities. I do have the backplane pulled out of circuit with 3 of the registers inserted. And forgive the camera movement here, but if I back up, you can see I've got all of the LEDs in view here. I've got this set up to limit to 1.5 amps and 5 volts. And when I turn it on, typically all the lights come on. You can see I'm putting out 5 volts and drawing about 400 milliamps. But there are times when I press on this or put my hand on it somewhere and see it's gone into current limiting, and I'm drawing 1.5 amps on this now. But eventually it will go back down. If I touch or move or what have you, it goes back to its normal operation. So I still have something that's not quite right. The fact that it keeps climbing up to higher and higher amperages, something's not right here. Now nothing is getting hot. There are a couple of places that are actually getting warm, but nothing is getting hot. Of course, I'm down to 200 milliamps now, so there's really not a lot of current flowing through this. But something tells me something's wrong somewhere in here because of the current bouncing all over everything. So not every single solder joint is going to be good, I believe, and I believe a lot of it is going to be related to the power connections. Now, having said that, I also want to call attention to the fact that down here, I have nothing hooked up here to control what's asserting and what's not. So let me, and here I go current limiting again. Let me reset this in such a way that I'm not asserting anything, and let me see if I can get better control of this circuit. What I believe may be happening is I've got some, because of the floating inputs, I've got some issues with things not actually happening properly. Let me see if I can tidy that up a little bit. Okay, I took a moment to tie every one of my control signals either high or low. The reset clear is tied low, everything else is tied high, so nothing is actually asserting. And so now if I turn this on, I get a brief spike, but I end up below 200 milliamps. I almost said millivolts. 200 milliamps with all of the LEDs turned on. So the undefined inputs were actually creating a bit of a problem. Now if I take and now that's the clear, let me do the other way around. If I turn around and assert everything, yeah, the amperage bumps way up here to 1.15 amps. And then of course if I turn that back off, I'm no longer asserting. And so that's making a pretty big difference in my current draw, not just the LEDs, but the outputs off the ICs. But it's much more stable with stable control inputs. So that's a good thing. Now, that said, if I measure the voltage down here, let's try to do that without shorting it at them. I've got 4.94 volts. I'm outputting 5.01 volts. Talking about 70 millivolt drop here. That's not too horribly significant. But when I have everything asserting, that is a significant drop. That's a half a volt lost. So I believe I still have a power problem here to solve. And I believe I need to be able to put additional current down both sides of this board. Now, can I bodge? Well, here I've got 18 AWG multi-stranded wire. And I believe that this is just going to be a hair too thick to put on the back of this board. This is 30 AWG, and this is wrap wire, which is typically used for bodging, but it's still going to have a pretty significant voltage drop as we go through that backplane. The last one to look at is my normal hookup wire, and I managed to grab orange, it looks like, but this is 22 AWG, and the voltage drop for this is small enough that I believe if I put this on the back of the backplane as a bodge to carry power, I will be in pretty good shape here. Now, with that said, I don't believe I have a ground problem because the ground is stitched together pretty darn well across that backplane, but power is not. And so adding something that's a little bit more substantial than a 0.3 millimeter wide trace, I think is likely going to help with the current draw and the voltage drop across this backplane. Let's give this a try. I've never done anything like this before, but what I did is I cut a piece of wire that's long enough to make it all the way down to the bottom down here, and I've got a little bit of extra. And so what I want to do is I want to weave this back and forth to all the different VCC connections up one side, tie it into the actual power input over here, tie it to the two outputs, and then down the other side over here. What I don't want to do is and this has picked up a lot of dust, what I don't want to do is I don't want to cut and have multiple connections in each one of these locations. So I am going to likely try to melt my way through the insulation here as I go along. I'm not exactly certain how that's going to work, but we'll see. First, the order of business is to identify where each of these different VCC connections are, because I really don't want to end up shorting this. So I'm going to be working down the left side. And VCC is towards the bottom and towards the outside. So VCC is towards the bottom and towards the outside as I'm working my way down. So here's the bottom, towards the outside and towards the bottom. So those are my first two connections over here. I'm going to try to zoom in a little bit, see if I can get that aligned right, and work on getting the soldering iron warmed up and ready to go. Okay, let's see what we can do here. The first thing I want to do, I don't know if you can see this particular pin right here, but I think I want to add solder to that and to make it a nice big mound on which I can actually make this connection. Okay, so that one's mounded up pretty good. And so the next thing is, can I get this attached in there? And yeah, that looks like it's going to work there. And so now the next step is going to be this pin right there. And once again, let's mount that up. That does not look good to me. Now, the question is, well, I did not get a good connection there, number one. And number two, did I bridge that? And I might have bridged it, which makes things even worse. Yep. So I bridged it, and not only did I bridge it, but I didn't actually make the electrical connection I needed. So this may end up turning into a bit of a mess. Okay, that's good. Well, it looks reasonably flat. Now I gotta check to make sure that I understand which connector is my VCC. Nope, not on that side. It's gonna be on... Alright, so VCC is the square terminal, and that's gonna be for both of these, so I should be able to get those locked in pretty easily. Once again, I need to look and see where VCC is for the main input. Oh, I need to get that capacitor too. Both of those are the square ones. Okay, now I've got to check again, the square connection and square connection. So more towards the top, more towards the bottom. So, okay. I managed to make this connection here to the wrong place, which means I've got to disconnect here. So I can put some heat shrink over this and reset. So let's see what I can do here. Well, the cross connection and the heat shrink tubing only took a couple of minutes to sort out. The rest of this went without a hitch. So let's get to the end where we talk about how to test this. Well, I think that's complete. And I really don't want to have to do that again. Definitely not fun. But most of that sits flat. And so now I just need to break out my power supply again and redo that previous test and see if, while I am asserting everything out onto the bus, if I get a significant drop in voltage. Let me get that set up. Okay, I'm set up here with my power supply again. I've got my control signals all tied definitively high or low. The reset is high. I'm sorry, I take that back. The reset is low. That's here. And the asserts are all tied high, meaning nothing is asserted. So now when I turn this on at 5 volts, I'm only drawing 200 milliamps, basically 1 watt here. If I switch this so that everything is asserting, no material change in the amperage pull. It's a little bit lower. Now I'm at 150 milliamps, 194 milliamps. And so if I go back and forth depending on what lights are on and what the values are, I finally have 1 amp there. And it's actually gone into current control. I'm not going to be able to say this is totally solved because of that one incident, even at 0.6. But I am going to be able to say that it is significantly better. I'm checking to see if things have heated up at all. And the ICs are ice cold. There's no warming at all happening here. Overall, I think this is a much better situation for delivering power to the boards. Next, I got to put it back into the full build and see if I can drive that off of my USB back here. This is the normal connection that I would use. So I want to be able to drive the entire build from that. Let me get that hooked up. Okay, the last task here is to go back to the start of the video where I was powering from directly the USB way up here, directly off the USB, which delivered exactly 5 volts, 2.4 amps of power. And if you recall, it would never come out of reset. So now when I power on the circuit, it does actually come out of reset now. And if I put it into run mode, program counter appears to be counting properly. I believe this is the correct pattern for R1 and R2 registers. So that also means that I got everything hooked back up right, amazingly enough. So I can slow that down, speed it up. Nothing is putting it into reset. And that's a good thing. So I'm going to call this with an asterisk by it, solved. At least I believe I have this settled for now. A quick word about the tests that I was doing prior. There is no logical situation in which all 6 buses on any one of these registers is going to be asserting at the same time. And certainly not all the registers asserting onto the same bus at the same time, which I believe is partly what was causing some of my current issues. So I'm going to put that asterisk there because I may end up coming across this again, but I think I have this largely solved. If there is something, it's going to be far more obscure and it's going to take a lot more troubleshooting to get to the root of that. Okay, I can't even begin to tell you how thrilled I am to have that settled, or largely settled, or mostly figured out. Certainly it is a huge step in the right direction for me and for this build, in order just to make sure that I'm not going to have any power problems. Now that said, there are still some issues to solve here. I've got my replacement EEPROM that I still have to get to the bottom of that and get something figured out there. But I've got some timing problems on this board that I really need to get to the bottom of, and that I'm going to tackle next. I don't expect that's going to get solved in one video, or 2 might be a stretch. It's probably going to be 3 or 4. There's several things that I need to try to get sorted here and get to the bottom of all the timing issues, and that is going to involve more than likely replacing some of the ICs on the registers. More on that in a little bit. In the meantime, see you soon.